Molecular dynamics is a computer simulation method for studying the physical movements of atoms and molecules, and is thus a type of n-body simulation. The atoms and molecules are allowed to interact for a fixed period of time, giving a view of the dynamical evolution of the system. In the most common version, the trajectories of atoms and molecules are determined by numerically solving Newton's equations of motion for a system of interacting particles, where forces between the particles and the potential energies are calculated using interatomic potentials or molecular mechanics force fields. The method was originally developed within the field of theoretical physics in the late 1950s but is applied today mostly in chemical physics, materials science and the modeling of biomolecules. Because molecular systems typically consist of a vast number of particles, it is impossible to determine the properties of such complex systems analytically. MD simulation circumvents this problem by using numerical methods. However, long MD simulations are mathematically ill-conditioned, generating cumulative errors in numerical integration that can be minimized with proper selection of algorithms and parameters, but not eliminated entirely. For systems which obey the ergodic hypothesis, the evolution of a single molecular dynamics simulation may be used to determine macroscopic thermodynamic properties of the system. The time averages of an ergodic system correspond to microcanonical ensemble averages. MD has also been termed statistical mechanics by numbers, and Laplace's vision of Newtonian mechanics, of predicting the future by animating nature's forces and allowing insight into molecular motion on an atomic scale. History. Following the earlier successes of Monte Carlo simulations, the method was developed by Alder and Wainwright in late 50s and Raman in the 60s. In 1957, Alder and Wainwright used an IBM 704 computer to simulate perfectly elastic collisions between hard spheres. In 1960, Gibson et al. Simulated radiation damage of solid copper by using a Born-Mayer type of repulsive interaction along with a cohesive surface force. In 1964, Raman published landmark simulations of liquid argon that utilized a Leonard-Jones potential. Calculations of system properties, such as the coefficient of self-diffusion, compared well with experimental data, even before it became possible to simulate molecular dynamics with computers. Some undertook the hard work of trying it with physical models such as macroscopic spheres. The idea was to arrange them to replicate the properties of the liquid. J.D. Bernal said, in 1962, I took a number of rubber balls and stuck them together with rods of a selection of different lengths ranging from 2.75 to 4 inches. I tried to do this in the first place as casually as possible, working in my own office, being interrupted every 5 minutes or so and not remembering what I had done before the interruption. Areas of application and limitations. Beginning in theoretical physics, the method of MD gained popularity in materials science and since the 1970s also in biochemistry and biophysics. MD is frequently used to refine three-dimensional structures of proteins and other macromolecules based on experimental constraints from X-ray crystallography or NMR spectroscopy. In physics, MD is used to examine the dynamics of atomic-level phenomena that cannot be observed directly, such as thin film growth and ion supplantation. It is also used to examine the physical properties of nanotechnological devices that have not been or cannot yet be created. In biophysics and structural biology, the method is frequently applied to study the motions of biological macromolecules such as proteins and nucleic acids, which can be useful for interpreting the results of certain biophysical experiments and for modeling interactions with other molecules, as in ligand docking. In principle, MD can be used for ab initio prediction of protein structure by simulating folding of the polypeptide chain from random coil. The results of MD simulations can be tested through comparison to experiments that measure molecular dynamics. of which a popular method is nuclear magnetic resonance spectroscopy. MD-derived structure predictions can be tested through community-wide experiments in protein structure prediction, although the method has historically had limited success in this area. Michael Levitt, who shared the Nobel Prize awarded in part for the application of MD to proteins, wrote in 1999 that CASP participants usually did not use the method due to a central embarrassment of molecular mechanics, namely that energy minimization or molecular dynamics generally leads to a model that is less like the experimental structure. Improvements in computational resources permitting more and longer MD trajectories to be calculated, combined with modern improvements in the quality of force field parameters, have yielded some improvements in performance of both structure prediction and homology model refinement. Without reaching the point of practical utility in these areas, most such work identifies force field parameters as a key area for further development. Limitations of the method are related not only to the parameter sets used, but also to the underlying molecular mechanics force fields themselves. A single run of an MD simulation optimizes the potential energy, rather than the free energy of the protein, meaning that all entropic contributions to thermodynamic stability of protein structure are neglected. The neglected contributions include the conformational entropy of the polypeptide chain and hydrophobic interactions that are known as main driving force of protein folding. Another important factor are intramolecular hydrogen bonds, which are not explicitly included in modern force fields, but described as Coulomb interactions of atomic point charges. This is a crude approximation because hydrogen bonds have a partially quantum mechanical nature. Furthermore, electrostatic interactions are usually calculated using the dielectric constant of vacuum, although the surrounding aqueous solution has a much higher dielectric constant. Using the macroscopic dielectric constant at short interatomic distances is questionable. Finally, van der Waals interactions in MD are usually described by Leonard-Jones potentials based on the Fritz-London theory that is only applicable in vacuum. However, all types of van der Waals forces are ultimately of electrostatic origin and therefore depend on dielectric properties of the environment. The direct measurement of attraction forces between different materials shows that the interaction between hydrocarbons across water is about 10% of that across vacuum. The environment dependence of van der Waals forces is neglected in standard simulations, but can be included by developing polarizable force fields. Design constraints. Design of the molecular dynamics simulation should account for the available computational power. Simulation size, time step and total time duration must be selected so that the calculation can finish within a reasonable time period. However, the simulations should be long enough to be relevant to the time scales of the natural processes being studied. To make statistically valid conclusions from the simulations, the time span simulated should match the kinetics of the natural process. Otherwise, it is analogous to making conclusions about how a human walks when only looking at less than one footstep. Most scientific publications about the dynamics of proteins and DNA use data from simulations spanning nanoseconds to microseconds. To obtain these simulations, several CPU days to CPU years are needed. Parallel algorithms allow the load to be distributed among CPUs. An example is the spatial law force decomposition algorithm. During a classical MD simulation, the most CPU-intensive task is the evaluation of the potential as a function of the particle's internal coordinates. Within that energy evaluation, the most expensive one is the non-bonded or non-covalent part. In big O notation, common molecular dynamics simulations scale by if all pairwise electrostatic and van der Waals interactions must be accounted for explicitly. This computational cost can be reduced by employing electrostatics methods such as particle mesh Wald, P3M or good spherical cutoff techniques. Another factor that impacts total CPU time required by a simulation is the size of the integration time step. This is the time length between evaluations of the potential. The time step must be chosen small enough to avoid discretization errors. Typical time steps for classical MD are in the order of 1 femtosecond. This value may be extended by using algorithms such as shake, which fix the vibrations of the fastest atoms into place. Multiple time-scale methods have also been developed, which allow for extended times between updates of slower long-range forces. For simulating molecules in a solvent, a choice should be made between explicit solvent and implicit solvent. Explicit solvent particles must be calculated expensively by the force field, while implicit solvents use a mean field approach. Using an explicit solvent is computationally expensive, requiring inclusion of roughly 10 times more particles in a simulation. But the granularity and viscosity of explicit solvent is essential to reproduce certain properties of the solute molecules. This is especially important to reproduce kinetics. In all kinds of molecular dynamics simulations, the simulation box size must be large enough to avoid boundary condition artifacts. Boundary conditions are often treated by choosing fixed values at the edges, or by employing periodic boundary conditions in which one side of the simulation loops back to the opposite side, mimicking a bulk phase. Microcanonical ensemble. In the microcanonical, or NVE ensemble, the system is isolated from changes in moles, volume and energy. It corresponds to an adiabatic process with no heat exchange. A microcanonical molecular dynamics trajectory may be seen as an exchange of potential and kinetic energy, with total energy being conserved. For a system of n particles with coordinates and velocities, the following pair of first-order differential equations may be written in Newton's notation as the potential energy function of the system is a function of the particle coordinates. It is referred to simply as the potential in physics, or the force field in chemistry. The first equation comes from Newton's laws. The force acting on each particle in the system can be calculated as the negative gradient of. For every time step, each particle's position and velocity may be integrated with a symplectic method such as Verlet. The time evolution of an is called a trajectory. Given the initial positions and velocities, we can calculate all future positions and velocities. One frequent source of confusion is the meaning of temperature in MD. Commonly we have experience with macroscopic temperatures, which involve a huge number of particles. But temperature is a statistical quantity. If there is a large enough number of atoms, statistical temperature can be estimated from the instantaneous temperature, which is found by equating the kinetic energy of the system to nkBT2, where n is the number of degrees of freedom of the system. A temperature-related phenomenon arises due to the small number of atoms that are used in MD simulations. For example, consider simulating the growth of a copper film starting with a substrate containing 500 atoms and a deposition energy of 100 electron volts. In the real world, the 100 electron volts from the deposited atom would rapidly be transported through and shared among a large number of atoms with no big change in temperature. When there are only 500 atoms, however, the substrate is almost immediately vaporized by the deposition. Something similar happens in biophysical simulations. The temperature of the system in NV is naturally raised when macromolecules such as proteins undergo exothermic conformational changes and binding. Canonical ensemble. In the canonical ensemble, amount of substance, volume and temperature are conserved. It is also sometimes called constant temperature molecular dynamics. In NVT, the energy of endothermic and exothermic processes is exchanged with a thermostat. A variety of thermostat algorithms are available to add and remove energy from the boundaries of a MD simulation in a more or less realistic way, approximating the canonical ensemble. Popular techniques to control temperature include velocity rescaling, the Nose-Hoover thermostat, Nose-Hoover chains, the Berenson thermostat, the Anderson thermostat, and Langevin dynamics. Note that the Berenson thermostat might introduce the flying ice cube effect, which leads to unphysical translations and rotations of the simulated system. It is not trivial to obtain the canonical distribution of conformations and velocities using these algorithms. How this depends on system size, thermostat choice, thermostat parameters, time step, and integrator is the subject of many articles in the field. Isothermal isobaric ensemble. In the isothermal isobaric ensemble, amount of substance, pressure and temperature are conserved. In addition to a thermostat, a barostat is needed. It corresponds most closely to laboratory conditions with a flask open to ambient temperature and pressure. In the simulation of biological membranes, isotropic pressure control is not appropriate. For lipid bilayers, pressure control occurs under constant membrane area or constant surface tension, gamma. Generalized ensembles. The replica exchange method is a generalized ensemble. It was originally created to deal with the slow dynamics of disordered spin systems. It is also called parallel tempering. The replica exchange MD formulation tries to overcome the multiple minima problem by exchanging the temperature of non-interacting replicas of the system running at several temperatures.